Good day, everyone. I'm Jorge Hernandez, and it's a pleasure to welcome you to today's episode of Encora Talks, optimizing GenAI model performance, continuous improvement strategies for production. Over the next 30 to 35 minutes, we talk about practical approaches for evaluating and improving the effectiveness of your GenAI models over time. We'll cover benchmarking techniques and strategies for improving the models. Now, seeing the slides. I don't. There you go. Thank you. Uh, so a little bit about myself quickly. I'm a principal machine learning engineer at Ancora. I've got 24 years of experience in tech. Here, I've led cross-functional distributed teams in delivering solutions for projects that millions of users use every day. We use both existing and custom machine learning algorithms. So that's a little bit about my work. But what this talk is going to touch upon is three things. One, the place of models in generative AI applications, how we evaluate their performance, and then how we improve said performance. So this is one of my favorite slides of any paper ever. This is what an ML application actually looks like. This is a product. And you can see in the middle that darker square, that's the ML. Everything else is not ML. And if you're thinking about evaluating performance and improving it, first thing I would say to you is go look at all the other stuff. There, your DevOps and software engineering knowledge applies. You don't have to worry about the ML. It's only when you look at that little square that you have to start worrying about everything else. And that is because modern generative AI applications are more complex than the non-AI applications. That little square includes data pipelines, feature stores, and model registries, monitoring and observability is needed for that square, and that's extra on top of the normal DevOps work and SRE work that you'd have to make for a non-AI app. And then modern generative AI applications are even more complex than traditional AI applications. They are almost always multimodal nowadays. They are often multi-cloud with all the complexity that involves. They involve CI and CD pipelines for prompts. It's not just code, it's not just data. Now you have prompts as well. And you have multiple kinds of databases almost all the time, SQL, NoSQL, graph databases, vector databases, of course, and the added complexity of having to do computation outside the CPU. And what does that look like? Well, this is what traditional MLOps on the left looks like. On the right, you can see that what we call foundation model operations. And then that little circle at the bottom is LLM ops. Now, foundation models includes everything that falls under the generative category. And of course, LLM ops, which is right now like the biggest ops concern is that score. But over time, that will change and you will move to a world where we get multimodal models that do everything and it's not just language. So on compute, like modern GPUs have grown even more complex. Now you can find that, for example, the G100 has multiple levels of memory and L2, different types of HBM, different kinds of cores, but Tensor and CUDA cores. And of course, you also have a multitude of different chips that you can use besides the GPUs. You have Google's CPUs, which offer lower precision and are faster and cheaper, but are less precise. So you got NPUs, a variety of architectures. Like we all know Apple's Neural Engine, which you find in the new MacBooks, and of course Qualcomm just came out with the new chip for the Surface laptops right now, and that uses Hexagon. It has its own NPU. And in the LLM space, we have stuff like Grok's LPU, which is 4 times faster than a GPU and cheaper, costs a third to generate the same amount of tokens that using Mistral that you use in a GPU. And literally a couple days ago, we have Edge coming in, and they use an ASIC that basically cooks in the transformer architecture. They call their chip Sohu, and they claim they can infer 500,000 tokens per second for Yama 70 billion. And obviously, that's an incredible number. So we'll have to see if they can actually deliver, but it'll be really interesting if they can. And then we also have stuff like Cerebras, where they built this huge ship, which is basically the equivalent of 20 times the size of a normal GPU, and it's basically a cluster on a chip used for very large training runs. They have been using it for the national laboratories. Argonne and Livermore, for example, I believe have used them for all kinds of simulations. So the world of compute is really, really wide right now, and that's something you got to take into consideration when you evaluate your models. Because if you're thinking about throughput, is it better to improve the model, change the model, or do I move to a more specialized piece of hardware? So you got to take those considerations into account. But if you are at the position where, okay, we've done everything on the DevOps side, we've done everything on the hardware side, we need more improvement, or you can't really move to new hardware because of the costs, then you move on to evaluating your model and seeing how you can improve it. And evaluating generative models is complicated. Uh, Multiple tasks require multiple different benchmarks. As I said, we're moving into a world where multimodal will reign. Uh, Curiously enough, audio and video modalities are harder to create automatic benchmarks for, but easier to do manual evaluation for, because our brains, human brains, excel at evaluating visual and auditive tasks. It's very easy for us to see when a video is not good enough. It's very easy for us to see when audio doesn't sound quite right, when we don't like it. And there are some benchmarks for audio caps, music caps, and music bench, for example, and for video as well, Eval Crafter and VBench, and I'll mention others further in the talk. But right now, the best recommendation is just play it by ear, just eyeball it. You'll do great if you do that. And LLMs, on the other hand, are harder to evaluate because we ask them to do so many different tasks that there is really no easy way for us to get from a single benchmark a good evaluation. So, what does the current landscape of measuring capabilities look like? What is a good measure? So, the standard is to use either the kind of stuff that researchers use to benchmark on, or to use the same benchmarks that we use to evaluate human beings. For example, have it pass the bar exam, or get into like pass those medical school um, exams. By these metrics, many LLMs are superhuman. They surpass humans. They do fantastic. The issue is that LLMs make mistakes that are different from those we make. Those tests are designed for people, and LLMs excel at some things that we don't, like recall. They're really good at remembering stuff, whereas we are faulty, and they don't take into consideration reasoning. Those exams are not good. So you get the sort of like spurious correlations that allow the LLM to get the right answer, even though it doesn't have the right reasons for it. And a good benchmark should have multiple observations per item and multiple items per construct to because we want fewer items. We can't tell if it's just this particular model or the particular selection of items that led to the answer. We can claim that an LM has its capability, theory of mind, causality, reasoning, planning. Uh, that's a claim about a construct. But we test it through an operationalization, and a good benchmark makes the link explicit and argues for the validity of that link. And of course, you always need a control. Like with every experiment, you need to be able to control every single aspects, isolate your variable, and then make sure that there's no noise in your measures. And of course, no measures that are not in the training data are really important. And I'll talk about it a little bit later on why. So psychology and cognitive science kind of help us lead the way in evaluation because the current landscape is not good. Um, as you can see on the right, that's Sonnet 3.5. It just came out. And if you look at those numbers, we're pretty close to fully saturating those benchmarks, which is like a very small set of canonical benchmarks which we have and mostly use. And like MMLU for general human understanding, GMSAK for math, and human evolve for code. And this set is not going to work for long because we've also suffered from not just saturation, which means basically that the numbers go so high, they pass the exam all the way, and there's no more way to measure how much better a model is uh, beyond that point, but because of contamination. The benchmarks are on the internet. Models memorize them because people training are not fully careful when they're cleaning their data. We've seen them. They perform much better on code problems, for example, released before the training data cutoff, and for the same kind of problems, if they were released after the cutoff, suddenly the same model is regressing and is barely above the baseline in the zero shot setting, which means there was contamination. They trained on those problems. They already seen them, and it's like giving them the answer to an exam. As I mentioned, they're very good at memorizing. So we are also seeing overfitting to benchmarks like MMLU and GSM-AK because everyone uses them for evaluation and during training, and that actually leads the model to learn those particular kinds of problems, but that may not generalize. And as a result, we've seen, for example, Scale AI came with a SEAL leaderboard. Those are private evaluations. They are keeping the data sets secret so that it doesn't leak and it doesn't, we don't see stuff like what you can see in this slide, where you can see that for GSM-AK and for math, there are multiple models that have this very suspicious sort of like left, and where they answer very similarly to the actual answers that you'll find in the data set in the benchmark. And for example, here you can see on the left how phi 3 for example, no, phi 2 actually way overfits GSM-AK and performs very poorly in GSM 1K, which doesn't kind of make sense if it were actually doing reasoning, if it were actually solving the problems the way we humans do. So that's a big problem. General suggestions on how to avoid this: you create your own data set for your own tasks, encrypt it, keep it secret, keep it safe. Scan any new evaluation data sets you see. Make sure that they don't have already the data that you use for training or fine tuning. Prevent data leakage. Like, don't send your benchmarks to OpenAI or Anthropic or Cohere through the API. Be sure if you actually need to do that, that you make sure that they're not going to train on those, because otherwise, over time, your benchmark will degrade because the model will just memorize it. And of course, you can use new benchmark like latest eval, Leukemia, Keval, LifeCode Bench, Termite. Other best practices include, as I said, create your private benchmarks. Use targeted benchmarks for your particular use cases. The benchmarks that are out there are more generic because they're mostly used by researchers for papers, and they're trying to test those constructs which are more generic. But your actual problem solving in an application, your actual task involves multiple of those constructs working at different levels of capability, and that those benchmarks might not fully capture exactly what you need. So building a benchmark that's targeted for your particular use case is better than using a generic benchmark. And of course, if you automate it using multiple other LLMs as judges, that's even better. It can help you use a bigger benchmark. It can help you do more refined kind of evaluations. And you should be careful. Only thing of is that if you use multiple LLMs, they don't all belong to the same family. They are not all OpenAI. They are not all Anthropic. They are not all Cohere, because those families share biases. So you want to be able to grab those biases to see them in the evaluation, and using the same uh, the same model family will not work. Uh, some of the new benchmarks, there are benchmarks for almost everything and anything you can think of, like Arc AGI that just came out, so $1 million prize for passing that one. And it's basically for AGI, but you have benchmarks for RAG, like RAG. There's also a competition right now in Kaggle for that one that Meta just put out. There's LifeBench, which keeps their full set secret. They just release it piecemeal. And there's Loft for long context. If you're worried about, yeah, I don't want to use RAG, I don't want to use any really complex things, I have access to a really long context model, this is the one you use for testing. There's MMLU Redux, which is a revised and annotated subset of MMLU. I suggest using that instead of MMLU. TOT for temporal reasoning. And of course, we get into like multidiscipline, multifaceted, multimodal stuff with MML World, Video MME, and natural plan for planning. If you plan to give it really hard questions, Olympic Arena, that's Olympic level, like mathematics and physics Olympiads level questions. And Wall Bench is, I think, one of the ones that for real use cases is the best. They actually took 1,024 tasks using different challenging real world user queries. This is an example. There are examples of what people actually ask these models to do. So you've evaluated your model. Now what? How do you actually go around making it much better? So the first thing is, don't touch the model. Let's try prompt engineering. This is the fastest way to improve performance. It doesn't require tons of compute. You do have to keep in mind that prompts are model specific. They might work from one model to the other in the same model family, but they probably will not translate from one family. Say, Claude will not work the same way with a prompt that's been fine tuned and designed for GPT-4. It's not transferable, so you do have to keep in mind, in particular, if you're using a multi-model system, that at some point your system has to rewrite the prompts so that you make the best use of each different kind of model. So keep that in mind. uh, Fortunately, there are many techniques for prompt engineering. There's tooling for it. DSPY is a great library for that. You also got, if you're working with Claude, Anthropic's prompt generator. And it's like a fantastic tool as well. And there are multiple guides and recommendations for how to work with particular models. Be sure to search the one that best fits your use case and apply what's there. But some best practices include defining success criteria that's specific, measurable, achievable, and relevant, and creating strong empirical evaluations. Here, you want them to be, as I mentioned, task specific. You want to make them automatable because larger is better. And just talking a little bit about prompting techniques. Uh, They can be divided into basically seven different kinds or families of techniques. Where you got like zero shot ones where you do role prompting, which is like pretending, telling the model, hey, you are a senior software engineer, help me debug this code. There's also asking them to ask themselves like questions. Then you got some few shot techniques, which is you use in context learning, where you give it examples, and you have stuff like KN, vote K, and Lens, where you ask them all to evaluate its responses from multiple examples. And then, of course, there's thought generation. Everyone, I think, has heard of chain of thought, but that actually branches out in both zero shot and few shot techniques. And there you have stuff like this, like constructive memory of thought, uncertainty, prompt mining. So you get a ton of different techniques there. And the thing about them is they all require multiple requests. You're making multiple API calls. You're calling the model multiple times. So that's something to keep in mind as compared to the few shot and the zero shot, which are single calls, even though they might be longer. So that's something that you have to keep in mind. And then, of course, it's ensembling really works in ML. And I don't think any practitioner has not used a random forest or at some point, or any other ensembling or another ensembling uh, algorithm, and you've probably seen it do wonders. So weak learners together become much better, and using techniques like max mutual information and more, and universal self consistency, you can exploit that for MMLs because they're statistical in nature, so they don't won't always answer the same way, and you can tweak the prompts from one to the other, and mixing techniques for with assembly. So that actually is one of the most promising areas. But of course, it's more complicated. It actually involves thinking about what the model is answering and how do we evaluate those answer backs. So you have to have really good task specific evaluations there embedded into your system. And then, of course, there's self criticism and the are you sure? Think about your answer. Uh, uh, can you make it better? That actually works very well. And of course, decomposition, which is three of thoughts, is one of the techniques used there. And well, I'm just going to mention two newer techniques. There are techniques that are appearing every day. There's this constant work on the field. So this one is buffer of thoughts. It uses a meta buffer to store thought templates, which is basically they're distilled from problem solving various tasks. Technique is very good if you can apply it to your specific tasks. In the case where you have multiple tasks and you go like, well, but I can't have a single set of prompts. Here, you can have multiple templates, which are adaptively instantiated with specific reasoning structures at the time where the user makes the request. And as you can see on the right, it has the advantage that it doesn't require multiple calls to refine and to find like the right prompt for the model, because it exploits precisely those templates, and those are managed dynamically, so they can be updated as your model, and as you fine tune the model, as you change your model from one version to another, and as the tasks themselves evolve or the questions your users ask you change. And the great part is it only requires about 12% of the cost of doing multiple prompting queries like in tree of thoughts or graph of thoughts. So that's a great this is a great new technique for those use cases where you have multiple similar but not quite the same tasks, and you want to improve your prompts there. And this is another one. This is for models that have visual capabilities. Um, Here, you can see on the right, there's this dialogue where they say start in this hexagonal map and move along these edges, move uh, down to the right, move down to the left, and so on and so forth. And in each node, there's like something, there's a thing, and at the end, they ask the model, what's there at the end of your path. And if you ask the models those kinds of questions, they do really badly. Like there are some for which, say, GPT-4 with chain of thought, it gets absolute zero. Just cannot do it. And here, these models can write code. They can generate code that actually makes images, and then they can observe those images and use them to reason the way we humans would for this problem where you just imagine yourself like walking like this in your head, and you picture and every single thing that is there, and you when you get back to a particular node, you know, oh, okay, that was there, so I know the answer. The same way, these models use Matplotlib and Turtle code that they themselves generate based upon the problem to generate an image which they then can use to solve the problem. And as I said, GPT-4 does gets zero on this, but using this technique, it goes from 0 to 92. So that's an amazing lift. And if you have this kind of problems where visual reasoning or spatial reasoning is useful, this is a technique that you definitely want to use because it's not that much more expensive than just doing chain of thought. And it actually solves the problem where chain of thought just basically does absolutely nothing. Now, uh, what is there beyond prompt engineering? Well, uh, in this case, I'm just gonna tell you to read this article, which is called "Optimizing AI Inference at Character AI." It's from Nasir, uh, and he's one of the authors of "Attention is All You Need." So, he's one of the smartest people in AI right now. And Character AI is handling right now about 20,000 inference queries per second, which is, to give you a perspective, is like 20% of the volume that Google search serves. And they're a small company. And they've basically done this by doing caching on the attention cache, the KBs, and quantization. They use quantization during training as well as during inference. So go ahead, read the post. It's 900 words. It's uh, it's a it's a mine of diamonds. It's like absolutely the best thing you could read if you really care about improving your performance. But okay, so you can maybe not apply all the stuff that goes there. Like those guys are wizards. So what happens for us mortals? What do we do? Well, there's fine tuning. We can quantize as well, and fine tuning is something that you must be sure that you only do if you absolutely have to. That is, if prompt engineering and doing RAG and improving your RAG with, say, hybrid search and a re-ranker model and other similar approaches, like what we just mentioned for prompts, they just fail. Like that didn't give you the lift you needed in performance. That didn't give you the reduction in hallucinations or confabulations, as I like to call them. There's a much better term. And what do you do? Well, you fine tune. It works best for complex tasks and use cases. And in this case, data is everything. It's just like training. Data is basically what determines whether or not you succeed. Uh, More is not always better. We've seen it, for example, when Illuthor recently released their Fine Web dataset. It was not that big when compared to, say, Common Crawl, and it actually is much better than using something like Common Crawl for a smaller model. Why? Because it's much cleaner, it's much clearer, and obviously, if you still need more data, and you go with synthetic data, but keep those quality standards high. Do parameter efficient fine tuning if you do, like LoRa or Dora, and quantize first. If you can afford to take that performance hit there, it will make it much cheaper and much faster. It will let you iterate and experiment much better. Probably it would be, I would suggest, experimenting with multiple versions of your data set. And if you need even more left, and particularly around accuracy and hallucination rates, you can go to Laminate and do Laminate memory tuning. And of course, for quantization, I suggest int 8 or int 4. Going lower will probably not be that easy. Yes, it's much cheaper, of course, but it does hit you enough in performance than you really have to start thinking seriously hard about the trade-offs between performance and cost and memory use and all that. So that is something that you need to be aware of. But the field is moving. You can always go check. I suggest always checking somewhere. I know it sounds kind of crazy, but Reddit, local llama, is a great subreddit. There's tons of knowledge there that if you go search, you will find surprising amount of little details there that will probably allow you to get that extra edge. And so, key takeaways. Generative applications are complex. The models themselves are just a tiny bit of the application. Think about improving the whole application. Like, we care about business outcomes. We care about products in the end. So think about where your bottlenecks are outside the ML. But once you decide that, hey, I've fixed everything outside, and now I have to look at the ML. Yeah, evaluating models is difficult. I suggest using private task-specific benchmarks. It takes time, it takes effort to design those benchmarks, but they pay for themselves in the end because they are much easier to use and they give you a much better benchmark of what your model and is going to act like in your actual use case. And then, of course, try prompt engineering first, and only if that does not work, should you fine tune. For quantization, I suggest using that if at all needed. Uh, that would be like my first step usually before fine tuning, and I would go to int 8, and then from there just see how that hits my throughput, my tokens per second, my costs, and yeah. So here are references for those that want to uh, take a look at where some of this information, extra information, can be found. I'll leave it up for a couple of seconds there, so that anyone that's interested can do a screen cap, and there you will find that that character AI post. I definitely suggest reading it. As I said, 900 plus words, less than 1,000, and amazing insights there around particularly caching and how to do it well, and when you can have some problems from doing cache, and how that actually uh, can prevent you from doing caching the full way and doing right and gaining those performance increases that the character AI team has seen, which are frankly really impressive for a small team. So I want to say thank you. It's been a pleasure. I'll move on to the Q&A, and yeah. Uh, so okay. First question: where do you see FMOps evolving in the next few years? Uh, as I said, right now we have this FMOps and LLMOps division, where most of the work is going into LLMs, but we are moving to a world where most models are going to be multimodal, where they will have visual capabilities. So what does that mean? It means that now your pipelines, your data pipelines, have to handle visual data. They have to be able to handle also video and maybe audio as well. So that makes stuff more complicated. That means you have to have more complicated benchmarks as well. And that means also that because of the increased capabilities, applications themselves will, be available for much more complex use cases. In this case, what I see happening is not only does that get more complicated, particularly in the monitoring, observability, and benchmarking part of the system and the ETL, but it also means that we're going to converge to a single stack, a single set of benchmarks, single set of technologies. Right now, you use different things for vision than you use for language. But once the models themselves converge into like a single set of capabilities that all of them can do, then it becomes possible to build tooling around that. So that is where I see things going. That convergence of tooling. Uh, okay. Oh, okay. How much farther can LLM improvements take us? This is a really interesting question. Uh, I think we might be hitting a little bit of a wall right now with the bigger models. What will happen is that they will gain much better capabilities for vision. We will see them gain much better capabilities for audio. I don't think we'll see that much of an increase on actual reasoning and planning capabilities. So with the right prompting techniques, we can work around that. I think that what we will keep on seeing and that we've been seeing is basically this incredible performance improvements. If you look at on the hardware and on the cost and memory and the speed of generation, if you look at the price of Sonnet 3.5 compared to the old Sonnet, it's better than Opus 3, and it's much cheaper. And I think this will get still. There's still room at the bottom to make these models run far more effectively, faster, with less energy, and with better precision. So there's still lots of room for improvement in the sense that we'll see error rates go down, hallucinations go down, memory usage go down. We'll see token generation speed go up. We'll see costs come down as well. We will not get that much for racing capability, particularly around reasoning and planning. But as you can see, we can work around that because there are a way of taking models that get a 0 to a 90 to a 92 with some techniques. So I would suggest, if for your particular tasks you really dive deep into these techniques and then just take advantage of the fact that all those teams out there at Meta, OpenAI, and Cohere, and everyone is working hard on making these things run much faster and much cheaper. I don't know if we have any further questions. Oh, for evaluation, that's really interesting. What I think we're going to see is far more mixed evaluations. Ones where you have to actually read and see, uh, read text, see video, and understand the interaction between the two, between the content and the meaning. And those will be far more interesting and harder to design for, but they will give us a much better perspective of what the edges of capability for the model are, or those edges of capability lie, where outside of those the models start failing catastrophically, like they just drop off of a cliff, like happens in most AI. And also, I think we will see far more task-specific benchmarks, which is good because those will be adaptable to our particular use cases for those of us working and designing and running the systems in production. So we will be able to see also uh, evaluations for stuff that is kind of like, I want to say, more abstract. There are currently it's very hard, for example, to measure if the world model of your model is really good, but there are techniques being developed right now to do that, to create those kinds of benchmarks where you're actually benchmarking stuff like not is this good at physics or math or a particular task, but is this thing good at thinking over time? Is the model good at having at creating a good world model? Is the model good at not just memorizing but actually inferring, reasoning? We'll see much better benchmarks for all those capabilities, and we will have a much clearer idea for the whole area is going and what the actual capabilities of the models themselves are. And any other questions? Uh, well, I think not. So it's been a pleasure. Thank you very much for attending this talk. Be sure to subscribe. There's tons of more content, and future Encore talks will touch on tons of other really interesting technical topics. So thank you very much. Have a great day, everyone.